This is Dr. Shankaraiah from Department of Physics. In today's presentation, I will discuss about long answer questions of Module 3, Lasers and Fiber Optics. So, this is question bank on Module 3, long answer questions. Okay. So, the first question, 11th question in Module 3 is describe an optical fiber, explore its construction and principle with a neat diagram. So, what is an optical fiber? Optical fiber is a cylindrical waveguide made of it's a cylindrical waveguide made of transparent dielectric which guides light waves along its length through total internal reflection. Okay. So we are saying optical fiber as a waveguide. Waveguide is a medium in which light can propagate. So optical fiber is a medium in which light propagates. So that is why we are saying optical fiber is a cylindrical waveguide, and this cylindrical waveguide is made of dielectric material. It can be plastic or glass, and in which we can transmit the signal, light signal, through total internal. So that is what is optical fiber. Then explore its construction and principle within it. Okay. So the principle for propagation of light in optical fiber is total internal reflection. Okay. So even if there is a bend of optical fiber, light can travel through the optical fiber even there is bend. Okay. So there is very small fraction of light that can escape from the optical fiber core. Most of the light will be received at the output end. Okay. So what is total internal reflection? Total internal reflection is a phenomenon in which light is totally reflected from a denser to rarer medium boundary, that is called as total internal reflection. Okay. So total internal reflection is a phenomenon in which light is totally reflected from a denser to rarer medium boundary. Okay. So what is denser medium? Denser medium is a medium which has higher refractive index. Denser medium has higher refractive index, and rarer medium has lower refractive index. Okay. So that is denser medium which has higher refractive index and rarer medium which has lower refractive index, and light will be totally reflected at this denser to rarer medium boundary, and that is what we call as total internal reflection. Using this phenomenon of total internal reflection, light propagates through optical fiber. Okay. So when does this total internal reflection occurs? What is the condition that is to be satisfied for this total internal reflection? Okay. So when we launch the light into the optical fiber, so there is a angle, critical angle. Okay. If the incident angle is less than critical angle, okay, there are three conditions. So there is a condition. So theta I, which is the angle of incidence, is less than theta C. Theta C is the critical angle. Okay. So theta C is critical angle. And theta I is angle of incidence. Incident angle. Incident angle. So theta I, they are saying it as theta 1 here. Okay. And theta R or theta 2 or theta R. This is angle of refraction or refracted angle. Okay. So when theta I is less than theta C, what happens when theta I is equal to theta C? What happens when theta I is greater than theta C? So these are the conditions. So angle of incidence is theta I. If theta is less than theta C, what happens? Theta is less than theta C, there is reflection and refraction. Partial of this light gets refracted and other partial light will get reflected. So there is both refraction and reflection when theta I is less than theta C. When theta I is equal to theta C, the light that is launched into the fiber will get reflected, and also the other part of the light will be grazing at the interface. So yeah, so this N1 is the denser medium, N1 is the denser medium, and N2 is the rarer medium. Okay. So rarer medium is lower refractive index, and N1 is denser medium, which is higher refractive index. So N1 is always greater than N2. So when theta is equal to theta C, the launched light will undergo reflection as well as partial light will be grazing at the interface between core and cladding. We will discuss what is this core and cladding. Okay. So basically these are the two layers of the optical fiber that is made up. Okay. So both theta is less than theta c and theta is equal to theta c, there is reflection and refraction. In theta is equal to theta c condition also there is reflection and also a refraction, but with angle of 90 degrees. So when theta is equal to theta c, when theta is equal to theta c, we need to point out that the angle of refraction is 90 degrees. Okay, but when theta I is greater than theta c, when theta I is greater than theta c, we will see the launched light undergoes total internal reflection. Okay, so for the light to undergo total internal reflection, we need this condition. That is, theta I must be greater than theta c. That is, the angle of incidence. The angle of incidence must be always greater than the critical angle. Only then we will have this total internal reflection. That is required for the light to propagate through optical fiber to have low loss of signal. Okay. Yeah. So these are the three conditions. And the most important condition required for total internal reflection is theta I is greater than theta c. That is where we have only reflection, no refraction. But in other two conditions, we know that there is refraction as well as reflection. Okay. So we have been saying here that there is critical angle and this angle of incidence must be greater than critical angle. So what is this critical angle? We can find out this critical angle using Snell's law. Okay, one can use Snell's law to find out the critical angle. Okay, so we will find using this Snell's law n2 sin theta 2 is equal to n1 sin theta 1, which here n1 theta 1 is theta I and theta 2 is theta r. So using this we will find out theta c as sine inverse n2 by n1. Okay, so sine inverse so we from this equation, from this Snell's law, we can find out sin theta as n2 by n1. Okay, so these are the three conditions that we have discussed just now. What happens when theta 1 is less than theta c and equal to theta c and greater than theta c? That is principle for the propagation of light in optical fiber. Coming to the construction of optical fiber has three cylindrical regions, right? So the innermost cylindrical region is called as core, and the next to the core we have cladding, and the outermost one is called buffer or sheath or coating, right? So these are the three layers of the optical fiber. Okay, so you can look at the diameter of each region. So the innermost core is having diameter around 8 micrometers to 62.5 micrometers, and around cladding diameter is around 125 micrometers, and coating or buffer or sheath is having around 250 to 900 micrometers. We can clearly see here that even though the optical fiber is bent, the light is undergoing this total internal reflection, but there may be partial loss of light when there is bent in optical fiber. Okay, so yeah, we have discussed about these three regions that optical fiber has. Okay, so the refractive index of the cladding must always be lower than the refractive index of the core. Okay, so yeah, so light launched into the core and striking the core to cladding interface at an angle greater than critical angle will be reflected back into the core. So that is what is total internal reflection. And so the outermost layer is called sheath or jacket buffer coating. It is a plastic coating given to the cladding for extra protection. Basically, it protects the optical fiber from physical and environmental damages. Okay. Yeah. So this is all together. To sum up, core is the innermost light carrying member. Cladding is the middle layer which serves to confine the light to the core. So it's very important. If you do not have a cladding, we may not, there may be loss of light, because if there is total internal reflection not satisfied, then the light will refract into the cladding and it will be lost. Okay, so the cladding, the important function or advantage of the cladding is that it confines the light to the core. Buffer sheath or coating will protect the fiber from physical and environmental effects. Okay. So the 12th question, derive an expression for angle of acceptance and of an optical fiber in terms of refractive indices of core and cladding. Okay. So we are going to derive the acceptance angle. Okay. So to derive the acceptance angle, we are going to consider one of the optical fiber, for example, step index optical fiber, right? So into which light is launched at one end, as shown in figure. Okay, so this is the step index optical fiber. So this is core and you have cladding, right? So the refractive index of core is n1. So the innermost one is n1 and the next to this is n2. Okay, so that is already given here. Okay, so let the refractive index of the core be n1 and the refractive index of cladding be n2, and we know that n1 must be greater than n2. Now, so we are going to launch the light into the fiber in some medium, right? So that medium refractive index is n0. Whatever medium we are using to launch the light into the fiber, that medium is going to have the refractive index n0. Okay, so there are three media now. Media where we are launching the light into the optical fiber, and the innermost one is core, and the next to the innermost one next to the core is clad. So these are the three media: launching zone, core, and clad. Okay. So using these three mediums, so we are going to calculate, find out the acceptance angle. Okay. We will define this acceptance angle in coming slides. Okay. Assume that a light ray enters the optical fiber at an angle theta I to the axis of the fiber. Okay. So we are launching the light into this optical fiber with an angle theta I. Okay. Theta I is the angle launching angle. We are launching the light into the fiber with the axis of the fiber at an angle theta I. Okay. So the ray refracts at an angle theta R and strikes the core cladding interface. Okay. This launch light refracts at an angle theta. So this is theta, that is the angle of refraction, and striking the interface of core. So this is core cladding interface, striking the interface of core at an angle phi. Okay. So this is phi. Okay. So now we have theta I, which is angle of incidence, launching angle, theta R, which is angle of refraction at with the axis of the fiber, and phi is the angle that is made by this light at the core cladding interface. Okay. So if phi is greater than critical angle, the ray undergoes total internal reflection at the interface. We know that only when phi, this angle phi, so when we discussed about these three conditions, theta is less than, greater than, or equal to theta c, those three conditions are between this core and cladding. So this is the interface that we have discussed about. So this is the interface, right? So this is the core cladding interface we have discussed. Okay, so this is the interface. This is core and that is cladding. Okay, so this is the angle of incidence at the core cladding interface. So in this case, we are taking that angle as pi. So pi must be greater than pi c so that the light undergoes total internal reflection. If pi is less than pi greater than pi c, only then light will undergo total internal reflection in this optical fiber. If not, there will be refraction and reflection. Okay. So this condition must be satisfied, that pi must be greater than pi c. Only then there is a very low loss of signal. Okay. Applying the Snell's law to the launching phase of the fiber. Okay. So launching phase of the fiber means okay. So we have core and then we have cladding. So this is the core and this is the cladding, for example. Okay. So this is the cladding. Okay. And this is the axis of the fiber. We are launching the light into the fiber. So this is theta I and this is n1, n0. Okay, so this is axis of the fiber and it undergoes refraction. Angle of refraction is theta R. This is n1 and this is n2. Okay, so we are going to apply the Snell's law to the launching zone n0 and the core n1 with an angle of refraction theta R. Okay, so applying Snell's law to this n0 with an angle of incident theta I and n1 with an angle of refraction theta R, we can write the Snell's law like this: n0 sin theta I, okay, n0 sin theta I must be equal to n1 sin theta R. So that means n1 by n0 is equal to sin theta by I by sin theta R. Okay, so we have applied Snell's law first to the launching zone and core. Okay, if theta increased beyond a limit pi, beyond certain limit, pi will drop below the phi c and light will escape into the cladding. Okay, so we are going to take the largest value of theta I will occur only when pi is equal to pi c. Pi cannot be less than pi c. Only pi must be greater than pi c. So we are taking the condition that at least pi must be equal to pi c, so that the light is in the core or at the interface. Okay, so this when the largest value of theta I can occur only when pi is greater than or equal to pi c. So that is why we are taking this condition. So if we take this condition of pi equal to pi c, okay, so pi equal to pi c, then what happens? Okay, let us see when pi is equal to pi c, because we require that we need that where light must undergo total internal reflection. Okay, so for that we need to take pi must be at least greater than or equal to pi c. Okay, so using this so in this Snell's law we have sin theta I by sin theta r is equal to n1 by n0. Okay, so now sin theta I by sin theta r is equal to n1 by n0. So this is what we got when we apply Snell's law to launching zone and core. Okay, fine. So to find out this sin theta r in terms of pi, okay, we are taking this triangle ABC. So this is the triangle, and using this right angle triangle, we know that the sum of the total angles is 180 degrees, or already there is 90 degrees. So sum of this theta r and pi must be 90 degrees, right? From this right angle triangle, we know that theta r plus pi must be 90 degrees, or theta r is equal to 90 minus pi. Okay, so now, so that in the theta r place I am going to substitute this. So sin theta r is equal to sin 90 minus pi. Sin 90 minus pi is cos. So that is how I got cos. Okay, so now I need to find out this cos pi. So because I am going to substitute in this equation, right? So in this equation, if I substitute sin theta I is equal to n1 by n0 cos pi. Okay, so to find out this sin theta I, which is the largest angle of launching angle, I need to calculate what is this cos pi. To calculate cos pi, I am going to apply Snell's law again to this core and cladding interface. Okay, so now second time I am applying Snell's law to core and cladding interface. So core is n1, which of angle of incident pi I, and so this is core, and cladding is n2, which is angle of refraction pi r. So this is cladding. Okay, so by using this Snell's law, applying Snell's law to this core and cladding interface, we can write down this. Okay, let me write down that. Okay, so n1 sin pi I is equal to n2 sin pi r. Okay, so now I am going to take the condition that pi I is equal to pi c. When pi I is equal to pi c, I know that pi r is 90 degrees. I know that from the earlier discussion. Okay, so I am going to substitute this condition in the equation. So that is n1 sin pi I am putting a pi c, and n2 sin pi r. Pi r is 90 degrees. So sin 90 is 1. So right. So sin pi c will be equal to n2 by n. So applying Snell's law second time to core cladding interface, we are going to find out this sin pi c is equal to n2 by n. Okay. Now we are going to use this sin pi c to calculate what is cos pi. Okay. Fine. Okay. So now let us calculate the cos pi value using this sin pi. We know using trigonometry, we know that sin square pi is equal to 1 minus cos square pi, right? So we can use that trigonometric condition, and we can write down the cos pi in terms of sin pi, because we know what is sin pi. Okay, so that is what we have done here. Sin square pi. Okay, so cos square pi is equal to 1 minus sin square pi, or cos pi is equal to square root 1 minus sin square pi. Okay, so square root 1 minus sin pi is n2 by n1, so n2 square by n1 square, so that is equal to n1 square minus n2 square by n1. So I'm taking out this n1 square outside the square root, so that is just n1. Okay, so now I know what is cos pi. So I can substitute this cos pi in the earlier equation. Okay, so I have the equation sin theta I equal to n1 by n0 cos pi. Okay, so I know what is cos pi now. So sin theta I, which is the angle of acceptance angle, equal to n1 by n0. So n1 by n0 cos pi is what? Square root. Let me write it. N1 square minus n2 square by n1. So n1 cancel out. So I'll get square root n1 square minus n2 square by n0. So sin theta is, that is the angle of incidence, is square root n1 square minus n2 square by n0. Where n0 is the acceptance refractive index of the launching zone. N1 and N2 are the refractive indexes of the core and cladding. Okay. Generally, we take launching zone as A, for which n0 is 1. So we can simplify this equation as square root n1 square minus n2 square, because n0 is, in general, it is A and refractive index of A is 1. Okay, so the acceptance angle sin theta A is square root n1 square minus n2 square, or theta A is sin inverse square root n1 square minus n2 square. So the angle of incidence is sin inverse square root n1 square minus n2 square. This is the acceptance angle, and I define the acceptance angle as the maximum angle that a light ray can have relative to the axis of the fiber, so that the light can propagate through total internal reflection in optical fiber. So this acceptance angle is the maximum angle that light ray can have with the axis of the fiber. If you are launching with an angle of incidence theta I greater than theta A, then no total internal reflection. Theta I must be less than or equal to theta A, then total internal reflection. If theta I is greater than theta A, there will be loss of light, because there will be refraction of the light. Yeah, so that is what I discussed just now. If theta is greater than theta A, there will be loss of light. If theta is less than or equal to theta A, then light will undergo total internal reflection, and whatever amount of input you are giving, that amount of output you will receive at the output. So rotating this acceptance angle about the fiber axis, you are going to get acceptance cones. Once light launched into the fiber inside this cone, that will undergo total internal reflection. Otherwise, there will be loss of light signal. Okay. So we have an acceptance cone. Acceptance cone is nothing but rotating the acceptance angle about the axis. Light that is launched into the optical fiber inside this acceptance cone will propagate through the optical fiber using under total internal reflection, and there will be low loss of light. Okay. What is a numerical aperture? Determine expression for numerical aperture of an optical fiber. The light gathering ability of an optical fiber is called as numerical aperture. Okay, so light gathering ability of optical fiber is called as numerical aperture, and we are going to determine the expression for numerical aperture. Okay, so numerical aperture is defined as light gathering ability, and the mathematical equation for numerical aperture is sine of acceptance angle. Okay, just now we have derived the equation for acceptance angle, which is sine inverse square root n1 square minus n2 square. Now we have defined a numerical aperture as light gathering ability of optical fiber, and mathematically we can write this as sine of theta A. Okay, so sine of theta A. So numerical aperture is sine of theta A, but theta A is sine inverse square root n1 square minus n2 square. Okay. So sine of sine inverse of x, sine of sine inverse of x is actually x, right? So that is why from this equation we are going to get numerical aperture as square root n1 square minus n2 square. So that is why I have written here. So numerical aperture is square root n1 square minus n2 square. Okay. So yeah. So you can write down this numerical aperture in terms of fractional refractive index. Here we have n1 square minus n2 square inside the square root. So n1 square minus n2 square you can write as a square minus b square. So if I consider this as a square minus b square, you can write as a plus b into a minus b. So I am going to multiply and divide by 2 n1 on both. So I am going to multiply and divide by 2 n1. Okay. So n1 minus n2 by n1, I am n1 minus n2 by 2 and n1 plus n2 by n1 into 2n. So this n1 minus n2 by n1 plus n2 by n1, this I am defining it as roughly equal to n1 because n1 is always greater than n2. n1 is greater than n2, so n1 plus n2 by n1, so basically you can write it as n1. Okay, so and this term I am defining it as so I am defining this, there is a mistake, so n1 plus n2 by 2 and this is n1 minus n2 by n1. So this I define it as fractional refractive index and n1 plus n2 by 2 is defined as n1. So okay, so then basically what I get is so numerical aperture is square root, so this I am defining it as delta and this I am defining it as n1 and outside I already have 2n. Okay, so basically that is n1 into square root 2 delta. So that is what I got here. Okay. So you can write down numerical aperture in terms of fractional refractive index. So fractional refractive index here we are defining it as we are defining fractional refractive index delta as n1 minus n2 by n1. Okay, so that is what we are defining it as fractional refractive index. Okay, high numerical aperture means good light gathering ability and good efficiency. Low numerical aperture means not very good efficient in gathering the light. 14th question, compare different types of optical fibers based on number of modes, propagation through core, medium and of an optical fiber. So we need to discuss different types of optical fibers based on modes. Okay, so based on modes of propagation, there are two different types: single mode fibers and multi-mode fibers. Single mode fiber has a smaller core diameter and it can support only one mode of propagation. That is why it is called single mode fiber, because small core diameter. Multi-mode fiber has larger core diameter and it can support multiple number of modes. Okay. So single mode step index fiber, here I am taking single mode step index fiber, So the refractive index profile is like it has step like profile. So if you look at the refractive index, it has step like profile. So that is why we are calling this fiber as step index fiber, and it can support only one mode. So that is why it is called single mode step index fiber. And how does the light propagate through this single mode step index fiber? So to describe this step index single mode fiber, it has core diameter around 8 micrometers to 12 micrometer and is made of germanium doped with silicon. Core is surrounded by a thick cladding of lower refractive index. Okay. So cladding is composed of silica lightly doped with phosphorus oxide. External diameter of the cladding is around 125 micrometers. And outermost one is sheath, opaque protective sheath. Okay. So the refractive index of the fiber changes abruptly at the core cladding interface, as we can see. So this is the core and this is the cladding, but this is the core cladding interface. At the core cladding interface, N1 is suddenly going to N2. Okay, so so that is step index optical fiber. The variation of the refractive index of a step index fiber as a function of the radial distance can be written as this: N of R is equal to N1 inside the core and N of R is equal to N2 inside the cladding. That is about this construction of this single mode step index fiber and propagation. How does the light propagate in this optical fiber? Light travels in a single mode step index fiber along a single path, that is along the axis. Obviously, it is the zero order mode supported by a step index single mode fiber. Both refractive index change and numerical aperture are very small for these single mode fibers. And this relatively small value is obtained by reducing the fiber radius and by making delta, the relative refractive index, change small. Okay, so the low numerical aperture means low acceptance angle. Therefore, light coupling into the fiber is difficult and costly laser diodes are needed to launch the light into this step index single mode fiber. Coming to the multi-mode step index fiber, so multi-mode step index fiber is very much similar to the single mode step index fiber, except that it has larger core diameter. Okay, so step index, so the refractive index profile always has this step-like profile, and this is multi-mode, so it can guide multiple modes, not only single mode. Okay, so the core diameter is around 50 to 100 micrometers, whereas the step index single mode one is around 10 micrometers, right? So this multi-mode step index fiber has large core diameter. That is the reason why it can support the multiple modes. And the cladding diameter is around 150 to 250 micrometers. Multi-mode step index fibers allow finite number of guided modes. The direction of polarization, alignment of electric and magnetic fields will be different in different rays modes. In other words, many zigzag paths of propagation are permitted in multi-mode fiber. The path length along the axis of the fiber is shorter, while the other zigzag paths path lengths are longer. Because of this difference, lower order modes reach the end of the fiber earlier, while the higher order modes reach the end of the fiber with some delay. Okay. Yeah, so that is about multi-mode step index fiber. You can also have multi-mode graded index fiber. In multi-mode graded index fiber, so the refractive index profile, this is the refractive index profile in multi-mode graded index. So the refractive index is maximum in the center of the core and decreases to match with the refractive index of the cladding at the core cladding interface. Okay, so this is a multi-mode graded index fiber. Okay, so the graded index is decreasing from the center of the core to match with the cladding refractive index. Okay, and because of this typical structure, this is some variation of the refractive index and core and cladding. How does the light propagate in graded index optical fiber? As a light ray goes from a region of higher refractive index to a region of lower refractive index, it is bent away from the normal. The total internal reflection is met, then the ray travels back towards the core axis again, continuously refracted. Okay, so the turning around may take place even before reaching the core cladding interface. Thus, continuous refraction followed by the total internal reflection and again continuous refraction towards the axis. Okay, continuous reflection, continuous reflection. So in the graded index fiber, rays making larger angles with the axis travels longer paths, but they travel in a region of lower refractive index and ends at higher speed of propagation. In multi-mode step index fiber, the light rays were reaching earlier. Some of the light rays reaching earlier, and some of them are reaching later. But in graded index fiber, all the light rays traveling through the fiber, irrespective of their modes of travel, will have almost same optical length and reach the output end of the fiber at the same time, because the light rays that are traveling with the longer path lengths are in lower refractive index. So that is why they will travel with higher speed. That is the reason why both lower modes and higher order modes will reach the output end at the same time. Draw the block diagram of optical fiber communication system and explain the functions of each block in the system. Okay, so this is a block diagram of fiber optic communication system. Basically, it has three major components: transmitter, optical fiber, and receiver. Okay, so in transmitter you have drive circuit. So we are going to give the input to the transmitter. So transmitter has drive circuit, light source, and you have optical fiber where the signal propagates, and you have receiver in which you have photo detector, amplifier, and signal restorer. Finally, you are going to get the output from the receiver. Okay, so let us see in detail what are these three major components and how are they going to help the light to receive at the output. Transmitter converts electrical signal to the light signals. Okay, so transmitter basically converts electrical signals into light signal. And the transmitter include modulator, encoder, light source, and drive circuits and couplers. Okay, once the transmitter converts the electrical signal into light signal, that light signal will be given as an input to the optical fiber through which signals propagate. Then this light signal will be received by the receiver. Okay, and it converts them into electrical signals again. So the receiver includes amplifier, decoder, signal restorer, and light decoder. Okay, so these are the three major components. The transmitter consists of a light source supported by necessary drive circuit. Basically, we are going to use LED, light emitting diode, that will convert the electrical signal into light signal. Okay, basically a transducer converts non-electrical message into electrical signal and is fed into a light source. First, whatever signal we have, so suppose if we have a audio signal, that audio signal will be converted into electrical signal. It will be converted into electrical signal by transducer. Transducer will convert audio signal into electrical signal. It can also convert electrical signal into audio signal, or if you have a video signal also it does the same, right? So first we are going to use the transducer to convert the audio signal into electrical signal, and that's a electrical signal will be converted into light signal by a light emitting diode, a semiconductor laser diode. Okay, so once we have this light wave, these light waves are modulated with the signal by varying the intensity of the light wave from the laser diode or LED. Analog modulation is achieved. Okay, we can also get digital modulation by flashing the laser diode or LED at on and off at extremely fast rate. Okay, so a pulse of light represents 1 and absence of light represent 0. So the message is basically in terms of zeros and ones. So if the receiver is programmed to recognize such digital patterns, it will reconstruct the original message. So the transmitter feeds the analog or digitally modulated light wave to the transmission channel, namely optical fiber link. The optical signal traveling through the optical fiber will get attenuated progressively and distorted due to the dispersion effects. Okay, so this is nothing but the loss of light signal through optical fiber. Therefore, repeaters are used at specific intervals to regenerate the signal. At the end of the fiber, an output coupler directs the light from the fiber onto a semiconductor photodiode, which converts the light signals into electrical signal. LED converts electrical signal into light signal, whereas photodiode converts light signal into electrical signal. Once you have electrical signal, this electrical signal will be converted into audio or video signal, which is given as input by transducer. Okay, so that is the block diagram of optical fiber communication system. Describe the step index fiber with a neat diagram and explain the transmission of signal through it. Okay, so just now we have discussed about this step index fiber. So this is the neat diagram of the step index fiber. So you must draw this fiber with core and cladding, right? So you have core and cladding. So here I have considered single mode. You can also consider multi mode. Okay, so step index fiber. So you must draw this refractive index profile. So this is core. In the core, so this is the core, right? So in the core you have refractive index N1, and in the cladding you have refractive index N2. So let me draw it neatly. So in the core you have N1 refractive index. So this is the value, and in the cladding you have N2 refractive index. Okay, at the interface it is going to N1 is going to change to N2. So that is why we have step index in this fiber. We have refractive index profile like a step index profile. That is why we are calling it as step index optical fiber, and these are the dimensions which I have discussed just now. Okay, we have also discussed the propagation of light in step index optical fiber, because there is only one mode, and we have to launch the light into this mode, because the numerical aperture and refractive index change is very small. Launching the light into this optical fiber, which is single mode step index fiber, is very difficult. So we need to use costly laser diodes. We can also discuss about multi-mode step index fiber. Multi-mode step index fiber has a larger core diameter compared to the single mode step index fiber, but because of this constant refractive index of the core, the light rays that are taking longer paths, will reach the output end at a later time, some time delay, whereas the light rays that are taking shorter paths will reach the output end with fast rate. Okay, so you will receive the signal. Partial signal will be received at some time, and partial signal will be received at some other times. Okay, if in the multi-mode step index fiber, because of so this is just now I have discussed. Because of this refractive index is constant in the core, longer light waves that are traveling in longer paths will reach the output end with time delay, whereas the light waves that are traveling in shorter paths will reach fast. Illustrate the advantages of optical fibers in communication system over ordinary fiber. Okay, advantages. What are the advantages of optical fibers? Okay, so there are different advantages of optical fibers compared to the copper wires. So first one is cheaper. Optical fibers are cheaper because it is made up of silica, which is available on Earth. It is one of the abundant material, and overall cost of the optical fiber system is lower than that of copper wire system. Okay, these optical fibers are small, light in weight, and flexible and strong. Okay, so this is another advantage. These are not hazardous. Optical fibers used in communication system are not hazardous, because a wire communication link could accidentally short circuit the high voltage lines, and the sparking occurring thereby could ignite combustible gases in the area, leading to a great damage. Okay, such accidents cannot occur with fiber links since fibers are made of insulating materials, for example, silica, glass or silica. Okay, so that is why these optical fibers are useful in communication system, because these are also not hazardous. Immune to EMI and RFI, electromagnetic interference and radio frequency interference. In optical fibers, information is carried by photons, not charge carriers, only photons. Photons are electrically neutral and cannot be disturbed by the high voltage fields or lightning, etc. Because information is carried by light waves are made of photons. Photons have no charge, they are neutral and they cannot be disturbed by any high voltage fields. Okay, so therefore these optical fibers are immune to this these signals, EMI and RFI. No crosstalk. Okay, communication is very secure because of optical fibers. The light waves propagating along the optical fiber are completely trapped within the fiber, within the core, and cannot leak out. Further light cannot couple into the fiber from sides. In view of these features, possibility of crosstalk is minimized when optical fiber is used. Therefore, transmission is more secure and private. Wider bandwidth. These optical fibers have ability to carry large amount of information. So that is why they have wider bandwidth. For example, telephone cable composed of 900 pairs of wires can handle 10,000 calls, whereas 1 millimeter optical fiber can transmit 50,000 calls. So that is the advantage of optical fibers. Low loss per unit length. Okay. So the transmission loss per unit length of optical fiber is around 4 decibels per kilometer. Okay. Therefore, longer cable runs between repeaters are feasible. If copper cables are used, the repeaters are to be spaced at an intervals of 2 kilometers. Okay. In case of optical fiber, the interval can be around 100 kilometers. So loss of signal is also very less. 18th question. Discuss in detail graded index for optical fiber with a neat diagram and explain the transmission of signal through it. Just now we have discussed about this graded index, multi-mode graded index optical fiber. So the difference between single mode and multi-mode is that multi-mode optical fiber has a large core diameter compared to the single mode optical fiber, and graded index, step index profile as a constant core and cladding refractive index indices, whereas in graded index optical fiber, the refractive index is maximum in the core and center of the core, and it decreases towards the core cladding interface to match with the cladding interface. So in graded index optical fiber, refractive index is constant in the cladding, but it changes. It is maximum in the core, center of the core, and decreases towards the core cladding interface. Okay, so this is the structure of the graded index optical fiber, and diameter is core is around 50 to 100 micrometers, and cladding is around 125 to 140 micrometers. Okay, so this is a refractive index profile variation in core and cladding. We have discussed the propagation of light in graded index optical fiber. In graded index optical fiber, the total internal reflection is met because of this refractive index change from the center to the core cladding interface, and all the modes, irrespective of the modes, whether they are taking longer path length or shorter path lengths, all the modes will travel with all the modes will travel and reach the output end at the same time. So that is the advantage of this multi-mode graded index optical fiber. What do you mean by attenuation in optical fibers? Write a brief note on different losses in optical fiber. Okay, so we are going to discuss about attenuation and optical losses in optical fibers. So when light signal propagates in optical fiber, there are two different types of losses: attenuation and distortion. Okay, so attenuation is nothing but the loss of amplitude of a signal, and distortion is nothing but the change in shape of the signal. Okay, loss of amplitude is attenuation, change of shape of the signal is distortion. So these are the two losses that occurs through the light signal when it propagating through this optical fiber. Attenuation can be defined as a ratio of output power of the signal to the input power of the signal that travels along the length. Okay, so if Pi is the input power that is launched at the end of the fiber, then PO is the output that is received at the other output end of the fiber, then PO is equal to Pi into exponential minus alpha L. So that means as this is the distance and this is the power, input power. So as the light travels more and more distance, the power will decrease exponentially, and so that is why we are writing this equation. PO output power is equal to Pi into exponential minus alpha L, where alpha is attenuation constant and L is the distance or length of the optical fiber. Okay, so taking logarithm to this equation, ln PO and log of Pi into exponential minus alpha L, will get ln Pi plus ln exponential minus alpha L. So ln Pi plus log of exponential of x is minus x, so minus alpha L. So ln PO is equal to ln Pi minus alpha L. So you can calculate L, which is attenuation coefficient, which you will find out as 1 by L into ln Pi by PO. So we can write down this attenuation coefficient in terms of decibels per kilometer, in the units of decibels per kilometer, which will come out as alpha decibels per kilometer is 10 by L log to the base 10 Pi by PO. For an ideal fiber, we will find Pi is equal to PO, because for ideal fiber, alpha is equal to 0, exponential of 0 is 1, so Pi will be equal to PO. Okay, so these are some losses of optical fiber, and the attenuation can be of two different types: intrinsic attenuation and extrinsic attenuation. Intrinsic attenuation coming from the impurities present in the material. So we are fabricating the optical fiber using silica, right, or plastic. So if when we are fabricating this optical fiber, if there are any impurities, then the light signal that is propagating through the optical fiber will be absorbed or scattered at the impurity. Okay, so then we will have this intrinsic attenuation. Extrinsic attenuation is also called as bending loss. So this extrinsic attenuation occurs when there is bend in the optical fiber. Because of this bend, there will be strain, and this total internal reflection will not satisfied, and hence there will be loss of signal, which is called as extrinsic attenuation. Distortion is nothing but the change of shape of the signal. So you can see clearly here. Okay, so at time t1 I have actually given this kind of the signal. So and then that has changed to this at t2, changed to this at t3, and it has become like this at t4. So basically there is a change in shape of the signal, which is called as distortion. The 20th question is that write a short note on the application of optical fibers in different fields. So optical fibers have many different applications in various fields. The first one is in medical industry. Because of this extremely thin and flexible nature, it is used in various instruments to view internal body parts by inserting into hollow spaces into the body. Okay, so it is used as lasers during surgeries, endoscopy, microscopy, and biomedical research, and also used in communication. Okay, so for transmitting and receiving purposes, because it has very low loss of signals. Compared to copper wires, optical fibers cable are lighter, flexible, and carry more data. These are also used in defense purpose because they provide high level data security, because there is no crosstalk if you use in optical fibers. Okay, and optical fibers are also used in industries. Okay, wherever if you want to see for in hard to reach places, you can use optical fibers because they are very thin and flexible, right? And we can view the damages or any problem is there in hard to reach places. They are also used in research and testing purposes in industries. Optical fibers are also used in broadcasting, for example, because they transmit high definition television signals which have greater bandwidth and speed. Okay, so these are also cheaper compared to the other copper wires. Okay, various broadcasting applications, also used in lighting and decorations. So we can use this optical fiber. It gives an attractive and an economical and easy way to illuminate the area, and that is why it is widely used in decorations and Christmas trees, because light can propagate through this optical fiber. Optical fibers are also used in mechanical inspection to detect any damages. For example, in any place we can use these optical fibers because they are thin and flexible. Okay, so these are some of the textbooks I have used, reference books, and to summarize, I have discussed the long answer questions on optical fibers from question bank. Yeah, thank you.
Like, share and subscribe. hit the bell icon for more updates.